So, hello everyone. I will talk today a little bit about Bayesian nonparametrics and specifically about the theory behind Chinese restaurant processes, which are relevant for some fields and algorithms in machine learning, and where we will look a little bit into the math behind it. So this is a general introduction, very briefly, about what the Bayesian methodology is about, and then we'll guide you into Bayesian nonparametrics, and from then onwards into these Chinese restaurant processes and what we are actually doing here. So for the introduction, machine learning, as you are well aware of, is based on data which has usually one or more of these following properties. It's in some way stochastic or generated from some complex, either non-deterministic or not yet fully understood process. Also, they will be noisily observed in some way, whether this noise is generally just stochastic noise of very little relevance, as in a lot of physical measurements, or whether this is a lot of noise where we do not really understand the process generating it. It might all be the case. And also we have cases where we have only partly observed data. We do not see everything we would like to see and we would like to know. In general, probability theory is a field of research which is focused on expressing and modeling uncertainties and finding in some way an appropriate data generating process. And therefore, probabilistic models try to be the best of both worlds, taking the necessities of machine learning for creating such processes, stochastic processes in some way, and modeling them in a way which transforms the information in the data into not just single number outputs, but something more general, let's say a knowledge or information about possible values, probable values, and telling us also in some way how much and how good information is contained in our data. This leads us to Bayes' theorem. This is the continuous way of expressing this theorem. We want to learn about an unknown parameter theta, which in some way describes the model, the process which we are trying to learn about based on the X, on the data which we have actually observed. And we do this by including a prior distribution. This prior distribution in some way expresses our prior information about this value, this theta which we would like to learn about, but it may also express our uncertainty about this value. Then there is the likelihood function. This is the part shared with most models. This is the part where we combine the information of our data with the parameters we would like to learn. And in this way, it evaluates the fittingness of our data to the model and also transforms the information contained with it to this whole probability scale. On the denominator here is the so-called marginal distribution. It generally doesn't tell us a lot. It is mostly just considered a normalization constant, which helps us to make this posterior probability, which comes out of there, again, a probability distribution function, which should have an integral of 1, and therefore this is mostly a normalizing constant. So we would like to learn about underlying parameters, properties, measuring how our models work based on the data. And why we are choosing this more complex Bayesian approach for this is explained in some way by this updating of information which we gain from Bayesian modeling. In general, having a likelihood estimation is what most statistical modeling is about. And this has the main disadvantage that we cannot include more than one data set, more than one data source. And immediately we see that machine learning, data science is a lot about combining different sources of information, about learning from one source of information and then learning in the second step about another one. And this learning is referred to as updating in this Bayesian context, and we will briefly look at this. So we would like to learn a posteriori about our parameter theta based on two different data sets, based on two different data sources. For this, we would originally require the joint likelihood function, where we include both of these data sources. However, it might not be the case that we have both of them available. It might be the case that one research unit has one data source, the other one has another data source, but not all is lost here. We can split up this likelihood into the part of the second data source and the part of the first data source, and combine the first one with the prior information as we've just seen before. And based on this, get posterior information, and then use this posterior of the first step, the first data source, and updating with it as the prior for the second part, the second likelihood part, in order to obtain the joint posterior. And this is mathematically the same. And this is one of the main reasons for Bayesian learning being valuable, because we can learn step by step, and this is mathematically identical as if we would have learned about everything in one go. So the visualization of this updating process, we start out with this red prior distribution. In the first step, we learn about this, we move in the direction of the data, and the distribution gets somewhat narrower and somewhat steeper because we learned more, we now got more information in it, and therefore we have less variation in our posterior. And adding the second data source provides us with this green posterior where we have learned a lot more 2 steps later, and we end up with the joint posterior. So why non-parametrics? We've just seen that this is about inferring a posterior distribution of a certain parameter. So one of the main disadvantages is that this inference about the parameter is clearly linked to the data via the likelihood function, and therefore the choice of this likelihood function is absolutely critical, as much as the choice of a prior distribution is. So likelihood functions, especially parametric ones, are limited with respect to their shape, with respect to their performance, with respect to the abilities which we would like to model about in the data. And we would like to have something more general. We would really like to consider any possible likelihood, not just the ones which are parameterized by certain sets of parameters, by closed form parametric likelihood functions which are known to us. And therefore, we would like to generalize this approach. So the notion of Bayesian nonparametrics in the first step of approaching it is, well, if we can have one parametric likelihood, let's try to model certain parts of the data with certain types of these parametric likelihoods, and then mix all of these together in a mixture modeling approach. This is pretty nice because within each part, we know what this parametric likelihood is like. We can still infer the parameter, the theta, and we also know that these weights, usually they have to sum up to 1, and therefore we obtain an approach which is pretty nice for us. This is the finite mixture model approach. This will get us close to any likelihood function we would like to approximate. However, the close is of course dependent on the number of these components, these p, and of course also on the chosen likelihood functions which we use for the approximation. So basically, in order to get infinitely close to any possible likelihood, we would need not just a finite mixture of such likelihood functions, we would need an infinite mixture of such likelihood functions. And this is the actual notion of Bayesian nonparametrics, mixing infinitely many likelihood functions. And this is done through a stochastic process, which allows us to add further components to our mixture models independent of how many we already have. So let's now look at these Chinese restaurant processes, and we will look at a very, very small restaurant, just 2 customers being there. And the first of our customers who enters, he can choose at any table he likes and choose any dish he would like for his table, the table number 1. The second customer then, in this stochastic process idea, has 2 choices. Either he can sit with customer 1 at table number 1 and share the dish which is already served there, or he might sit at a new table and choose a new dish for himself. The first happened with 1 over 1 plus alpha. The second happens with alpha over 1 plus alpha. So this was a very small, very cute little restaurant with only 2 customers. Let's look at a little bit larger setting. So we now have a slightly larger restaurant. We have 8 customers who have already chosen their tables. Customer 1, customer 2, and 5 sit at the first table, sharing 1 dish which is served there. Customer 3 has special taste and sits at his own table with his own dish. Customers 4, 6, and 8 again share a table and the dish served there, and customer 7 again chose a different table. So now, after all these 8 customers, customer 9 is entering the restaurant and has the following options. Can either sit at the table number 1 with those 3 guys, and this will happen with probability 3 over 8 plus the alpha, or choose the table number 2 with probability 1 over 8 plus alpha, and so on and so forth for the 3rd and the 4th table. Or also, customer number 9 has the option to choose his own table and his own new dish for this table, and then create a new table based on this. As we see, this alpha parameter in here has somewhat a steering effect for creating a new table, and based on how many customers we already have, the probability for opening a new table will always decrease. So we will now generalize this and look at the mathematical notation for this. So we we start out from our two customer Chinese restaurant process before we go to the infinite one. With two customers, we have two possible tables, and we would like to have the dishes on our table to actually be the different means of some kind of underlying normal distribution. We generate those means from an underlying normal distribution for the means. On the one hand, this is a conjugate prior approach for drawing mean values, mean parameters. On the other hand, it is important here that both of them are generated from the same underlying distribution. However, they are still different parameters, which will then encode different tables, different dishes. We remember we had this alpha parameter, and it controlled how likely it would be to create a new table, to open a new table. So therefore, based on this, we would like to draw a probability for opening a new table. And this is done through this beta distribution, which basically refers to the two probability scenario, which we've seen up above. And we will then draw an indicator, an auxiliary variable of an indicator, which is in itself Bernoulli distributed, therefore binomial with this probability and a size of 1. And we only add 1 because the Bernoulli variable would be either 0 or 1, but we want it to be 1 or 2 in the end, having table 1 or having table 2. As we have only two possible customers of all, there we will only look at the two table scenario. So in the end, for our data, we can, based on which table we have chosen, the corresponding dish on this table is the parameterization, the either mu1 mean of the first or mu2 mean of the second normal distribution with, in this case, for simplicity's sake, the same covariance structure, although we could as well have different covariances for both normal distributions here, which would then include the covariance matrix into the dish and into the parameters which we are estimating, which are to be different between the different components. So we've seen that we are using this beta distribution in order to end up with this probability. And we will now look at the generalization of the beta distribution, which is the Dirichlet distribution. In case you're not familiar with this distribution, it is the higher dimensional generalization of the beta distribution, and it works on the unit simplex in the way that on this unit simplex, always the parameter values chosen there have to sum up to 1. And based on the choice of the underlying parameterization, either this is centered if they're all identical, and the larger they get, the more this is placed or centered around the center with very little variation, very little chance of spreading out until the very ends, of having very unbalanced settings. So the higher these parameters, the more balanced and the more centered they will be. The more different these parameter settings, the more it will drop or turn in one direction, and focus on only a specific subdimension to become very likely, while the other two become far less likely to be observed. So in this way, we put different weights on different parts of the space. This is the three-dimensional way, but we can generalize this distribution for higher dimensions as well. And we will now require this Dirichlet distribution in order to encode k different tables with it. On all these k different tables, I'm still using the table analogon because it's easier to still keep it in mind what we're doing here. Each of the dishes served there will be encoded by a different mean of the underlying distribution. So now we're generating k different means, all still, as we can see, from the same underlying distribution, prior distribution for these different means of the dishes. The table weights are now generated by this Dirichlet process, and we see that alpha again has some influence there, and alpha has exactly this influence as we have seen in the case with the 8 customers and the 9s coming in, that it's regulating how the different tables, dishes are distributed between the tables and how easily it will steer to create a new one or not. Now these k different weights allow us to choose between k different categories, and therefore we're not sampling from a binomial but from a multinomial distribution in order to obtain the actual indicator of which group our observation will fall into. And based on this group indicator, we will then choose the appropriate mean, and in this way, most simply here, put this into a normal distribution, which just is different with respect to the means. This is still a finite mixture. We have here the k different components, the 8 different tables. There's no option of, or there's 4 different tables. There's no option currently of creating a 5th one. We are only using the ones which we have available, k different ones in this case. And we will now look at what this has to do with Dirichlet processes and why they are useful in the first place. So I said the normal distribution we chose for having a conjugate prior setting, so for keeping the structure of our distributions. And this is also the case for the Dirichlet process based on this alpha value. So the Dirichlet process, which we will then look into, which is this adding a further component based on how many components we already have. This is now the step we have seen from going from the 8th customer setting to the 9th and opening up now the option of creating a new table. This is from going from the finite mixture to the next step, the Dirichlet process. And in this case, this Dirichlet process actually allows us to keep the structure. We have an alpha which is updated, and we've already seen how it is updated. In every step, we add the number of customers which we have already grouped, and therefore opening up a new table, as we can see here, becomes less likely the more customers we have already grouped and the more information therefore we already have in our model. independent of how many groups there already are. So we include this part of the indicators of the already grouped data and add it to the original process, and in this way create our new updated stochastic process for generating this. So moving from the finite to the infinite, this is a daring step, and therefore we will take a little bit of a closer look at it. So we can be sure that it's conjugate, no worries about that. But what's actually happening here? So what we would basically do is that we would like to choose these different labels, having each of them one of the different groups which we already have, based on all the information, all the previous labels of all the data without the one which we are grouping now, and the alpha process. And this includes, and now here is the information of how many people are already sitting at the table, the NK, how many are choosing a certain dish, and considering how much people like a certain dish, it's more likely to end up at a table with a dish favored by a lot of people than ending up at the table with a dish favored by only a few people. And what is happening back there is alpha would be divided by the number of k. This is what's actually done in this Dirichlet distribution. And of course, if k, the number of components, goes to infinity, we are not just mixing a finite number of possible groups, we're making them infinitely many. This last part goes to 0. And therefore, we end up with what we've seen before, the number of people seated at a table divided by all people we've already grouped, plus the alpha. And therefore, this alpha and its size is strongly regulating how plausible it will be to open up another table. So how do we do this? We've seen the Dirichlet distribution. We've seen that this simplex is pre-made and that we're choosing in the simplex how to put the weights and which parts would be most reasonable. But now we still want weights which sum up to 1. Otherwise, the weighting would not be mathematically proper on the one hand. On the other hand, we have infinitely many of them. As we know from basic math, if we sum up infinitely many values and we still want to add up with a sum of 1, the values have to get smaller and smaller and smaller and smaller the further they get with summing them up. And therefore, we create this stick breaking process, which will be the prior instead of the Dirichlet distribution. So we start out with a stick of length 1. This stick of length 1 represents the total weights which have to sum up to 1. And those is the total sum of all possible subsets. Now of this stick, we break up the first part, which is the weight for the first table. And once we've broken up this first part, the rest of the stick still remains as the possible weights, the sum of possible weights for the other weights and all the other tables which have not been there yet. So in the next step, we break up the part which will correspond to the second table, and so on and so forth. So we start out with the stick with total length of 1. We break up the part which corresponds to the first table. The rest, the other part, will be 1 minus the weight for the first one. And now we take this one as the total length and we break up again the part which is the weight for the second table and keep the rest for all the others. And again, out of this, we break up the part which will correspond to the third table and keep the rest for all the others, and so on and so forth. Because it's always the rest where we're taking out the next proportion, we will definitely end up with something with the total sum of 1, and it will always be less likely from a certain part onward to open up another table once we already have a certain amount of tables. So this leads us to the Dirichlet process mixture. As we now have infinitely many possible values, we now have actually a continuous sum of things, and the continuous sum of things is of course the integral, and therefore we are actually integrating our likelihood function with respect to this data generating process, and this data generating process is the Dirichlet process, which has the part, the alpha parameter, how plausible it is to create new groups, and the underlying distribution. As said before, we are always drawing these mu's, these parameters from the same underlying distribution. This would be this G0 in this context. So depending on what we want to create as a model, we can choose for this G0 either something discrete. If we have count values, we can choose different Poisson distributions, which might be used in bioinformatics for next generation sequencing data, or we use different type of binomials for anything in the current epidemiological setting where we know how many patients have already been tested in total and mixing all of these together. Or we have something continuous, which might be either univariate or multivariate, and we mix up such distributions. Generally, whenever we have something continuous, the most easy distribution to work with would be the normal distribution. However, if we have only a limited domain, then it might be more reasonable to choose a gamma distribution or uniform distribution instead. So this leads us to the hierarchical formulation of the Dirichlet process mixture, which is we want to model our data based on underlying parameters and an underlying phi, which is a parameter, all the parameters which are not differing between the groups. As I said before, we have the same covariance matrix for all groups, then this would be one of these phi's. Otherwise, all the ones which are different between the groups are the theta i's indicated with the groups. The theta i's therefore depend on the underlying distribution G, which is generating according to this Dirichlet process, as we've seen before, creating a new group based on this alpha regulating parameter and whatever the structure of the underlying likelihoods from which we sample this might be. And therefore, we have joint priors of these phi's, which is the parameterization of the prior of the Dirichlet process, the alpha itself, and the phi's, the independent parameters, group independent parameters of the process up there. So this leads us to the mixture representation of our parametric densities, because all of these things are actually parametric. We just mix infinitely many of these distributions here, And we've already seen that we can create these weights appropriately by using this stick breaking prior. To give you a little bit of an outview, there's also an extension of these Chinese restaurant processes referred to as the Indian buffet process. In this case, if we do not want to uniquely be stuck with a single table and a single dish served on this table, but for each data point, we would like to have the option of having several dishes available, but putting weights on the preferences which we have for certain dishes, and therefore having a combination of dishes for each of our data points. Then this is rather referred to as the buffet from which we are choosing as the analogon. And therefore, in this case, we open up this clear indicator function and instead create a whole set of weights which we're generating there and the whole set of possible indicators groups to which these correspond. All the rest is the same as we've seen before. And therefore, to summarize this, these Chinese restaurant processes, this non-parametric Bayesian modeling with Dirichlet processes, is adaptable for all types of Bayesian hierarchical models, in particular for all nonlinear, linear, generalized or regularized regression models, for anything that's multiple stage modelings, such as instrumental variables or structural equation models in the Bayesian context, for any type of classification, and of course, most naturally, clustering, because clustering in itself in the Bayesian approach is already a mixture-based methodology. And therefore, this is used in modeling text, in modeling, clustering biological data, microarray, next generation sequencing, in modeling biodiversity, also epidemiological data nowadays in econometrics, or in fields such as image reconstruction or natural language recognition. So that was it. Thank you very much for your attention and looking forward to any questions there might be.